So in section 12.4, we're talking about probability of disjoint and overlapping events. So what are you going to learn today? You're going to find the probabilities of compound events, and you're going to use more than one probability rule to solve real-life problems. So if we're looking at compound events, here we go. When you consider all of the outcomes for either of two events A and B, so we have two different events, you form the union of A and B, as shown in the first diagram. When you consider only the outcome shared by both A and B, then you're only looking at the intersection of A and B, which what do they have in common, as shown in the second diagram. So these two, the union or intersection of two events, is called a compound event. To find the probability of A or B, you must consider what outcomes, if any, are in the intersection of A and B. Two events are overlapping when they have one or more outcomes in common, as shown in the first two diagrams. You can see here in the middle, and here in the middle, they have things in common. But in the third diagram, the intersection of A and B is empty. They don't combine at all. Two events are disjoint or mutually exclusive when they have no outcomes in common, as we said here in the third diagram. Here's your core concept. If A and B are any two events, then the probability of A or B is the probability of A added to the probability of B, but then you have to subtract A and B. Now you're like, why do I have to subtract? Because of this. Here's your study tip. Let's put it here. There we go. If two events, A and B, are overlapping, then the outcomes in the intersection of A and B are counted twice, as you saw in that first diagram. Because they're counted twice when they're added, you must subtract the sum of them added, because it's been counted twice, so you have to subtract it. If A and B are disjoint events, then the probability of just the probability of A added to the probability of B. So we're going to find the probability of a disjointed event. So a card is randomly selected from a standard deck of 52 playing cards. What is the probability that it is a 10 or a face card? So A or B. So we want the probability of A or B, which is just the probability of A plus the probability of B. So how many are, what is the probability that a 10, it is a 10. Well, how many 10s are there? There's 4. So that'd be 4 out of 52. Plus, or a face card. Well, how many face cards are there? There are 12. And you can just add right away. You're just going to add 4 plus 12, which gives us 16/52, which simplifies into 4/13. You can leave it like that, or you can give me approximately 31%, or 0.308. Notice that none of these overlap, because a 10 cannot be a face card. Example 2. A card is randomly selected from a standard deck of 52 playing cards. What is the probability that it is a face card or a spade? So what you have to do now is you want probability of A or B. So if we add them together, now let's think, a face card. How many face cards are there? Well, there are 12. So the probability of A is a face card. So that's 12/52. Plus the probability of B. And we want to know a spade. Well, if you don't know how many spades there are, we go from 2 to king and then the ace. So there are 13. But wait a minute. We have a problem. Some of those overlap. So what you have to think of is what overlaps, because we've counted it twice. We counted it here and here. So we want to know, are there face cards that are also spades? Sure there are. There's the king of spades the queen of spades, and the jack of spades. Ace is not a face card. So we have 3 that we counted. So we're going to subtract 3 50-seconds. So all you're doing is adding 12 and 13 and then subtracting 3. So that's going to be 22 50-seconds, which simplifies into 11 26ths. Or you can give me an answer of approximately 0.423. If you wanted to make a diagram, you could have, and saw this. We have 12 total here. We have 13 total here. As you can see, you counted 3 of them twice, so you have to subtract the 3. So in example 3, we're going to use a formula to find the probability of A and B. Out of 200 students in a senior class, 113 are either varsity athletes or on the honor roll. There are 74 seniors who are varsity athletes and 51 seniors who are on the honor roll. What is the probability that a randomly selected senior is both on varsity, or a varsity athlete, and on the honor roll? So we first have to start by writing a general formula. So I'm going to start by A. Let's do A is selecting a senior who is on varsity. So varsity, I'm going to let be event A. B, I'm going to do honor roll. So what do we know? The probability of A is varsity athletes. So there's 74 varsity athletes out of 200. The probability of B, which are 51 who are on the honor roll, and the probability of A or B, now remember, it says varsity or on the honor roll. It doesn't say both, so they're either on one or the other. Is 113 over 220. So we're going to write our general formula. P of A or B, which we already have done this formula. Because remember, these are not mutually exclusive or disjointed. They're shared. So our general formula is the probability of A plus the probability of B minus the probability of A and B. So we know A or B is 113 220ths. We know the probability of A is 74 200ths, and the probability of B is 51 200ths, minus the probability of A and B, which we don't know. So that's what we need to find. So we're going back to our good old algebra skills. So what do I want? I want to find this, so I get it by itself. So I'm going to add the probability of A and B to the other side. So the probability, I'm just using my simple rules of inverse operations. So I'm moving it over here to the left side of the equation. I'm going to move the 113 220ths to the right, which turns into minus. So I'm going to add 74 200ths plus 51 200ths. That gives me 125 200ths. Minus the 113 220, I'm sorry, should be 200ths, not 220ths. I just realized this the whole time. This should be 200. Let's fix my mistake. We all make mistakes. All right, so subtracting 113 200ths, which gives us the probability of A and B, which gives us 12 200ths, which simplifies into 3 50ths, or 6%. So what is the probability that a randomly selected senior is both varsity and on honor roll? It's about 3 out of 50, or 6%. Our last example is challenging, using more than one probability rule. In the first 4 sections of this chapter, you have learned several probability rules. The solution to some real-life problems may require the use of 2 or more of these probability rules, as I'm going to show you now. So in example 4, the American Diabetes Association estimates that 8 3/10% of people in the United States have diabetes. Suppose that a medical lab has developed a simple diagnostic test for diabetes that is 98% accurate for people who have the disease and 95% accurate for people who do not have it. The medical lab gives the test to a randomly selected person. What is the probability that the diagnosis is correct? Well, we have to figure out what probability of A and B would be. So I'm going to let the event A be a person with diabetes. B is going to be a correct diagnosis. Now, the probability of B depends on the occurrence of A. So these are dependent events. So what does it say? When A occurs, so when A occurs, then what? If A occurs, the person has diabetes, 98% of the people are accurate, or the test is accurate for those people. So we know the probability of B given A is 98%. Now, when A does not occur, the probability of B is 95%. So we're going to represent that as 95 or 0.95. So a lot of you are visual people. So I'm just going to give you this. This is going to help you, I believe, because it's hard to even know in this problem. Where do I start? What do I do? So let's just say you're a person in the United States. We know that from our information that 8.3% of people in the United States have diabetes. So event A is a person that has diabetes. Now A bar, remember this, we can use complements of events A and B to complete the diagram, where A bar would be a person who does not have diabetes, and B was a correct diagnosis, so B bar would be an incorrect diagnosis. So if we know 8.3% of the people have diabetes, 91.7% of the people do not. Now, if in A, we know that 98% of the people are correctly diagnosed. That means B bar will be 2% are incorrectly diagnosed. We know that of those who do not have diabetes, from our information in our given, 95% are correct diagnosis. That means 5% are not. So, to find the probability that the diagnosis is correct, let's actually follow the path. This is what's important. Let's follow the path. A diagnosis is correct. We want to end up here and here. So what paths do we have to follow? We have to follow this path and this path. We then have to follow this path and this path. So what do I want? I want the probability of B, a correct diagnosis. How do I get there? Well, the first path would be the probability of A and then B. Does that make sense? A, probability of A, event A, and then probability of event B happening. Plus the probability of A bar, which means they do not have diabetes, but then the correct diagnosis, so and B. So what is the probability of A then B? Well, you're going to take 0.83 times 0.91. Or, I'm sorry, 0.083 and then 0.98, so 98% multiplied by 8.3%, plus A bar, which means 91.7% of the population, so 0.917, multiplied by B, which is the correct diagnosis of 0.95. That gives us approximately 0.952. So, what is the probability? About 95.2% the diagnosis is correct. And your vocab words are these 4 words.